Do the quiz. There is a quiz. It's not difficult. Do the quiz. All right. Hi, everyone. So today I want to go back to thinking about the that. So I want to go back. Hello, to the quiz. So I'm gonna. It's not like the due date is not until 4, so like no hurry. I want to go back to computing the computational complexity of the fib of n function. So that was kind of like this. So we return 1 for small ones, and then we return fib of n minus 1 plus fib of n minus 2. To remind people, so how many people have seen the Fibonacci sequence like before I told you about it? So like, yeah, so like most people. So I'll tell you about the rabbits and stuff now, I guess. So it's like this, and the idea is that this is the sum of the two preceding ones, and the scenario would be so you start with one pair of rabbits, I guess. So it's a little bit annoying because you have to say pair of rabbits, and then we say rabbits mature and start reproducing at 2 months, I guess. And each pair of rabbits produces another pair, so mature pair of rabbits, I guess. Pair of rabbits. So we'll say, so months 1, you'll have 1 pair, and then months 2, you still have 1 pair, because those are still not mature. And then at this point, you're gonna start saying, okay, so how many rabbits are you gonna have at month 3? Well, it's that those have now reproduced, so you have 2 pairs. And then because you have to start here, so now you have 2 pairs. And now the question is, what happens at month 4? Well, at month 4, you have the old rabbits over here, which are going to produce another pair. And then you have everything except this pair. So like 1 pair over here that's also going to reproduce. So that's going to be 1 plus 2. So then next time, so over here you have the two ones that are not mature, but everything else is going to reproduce. So 2 plus 3. And so on. Right. So that's kind of the idea. So the other way of thinking about it is like with some linear algebra, you can show that fib of n is a round of 5 to the n divided by square root of 5. So you can just show it with linear algebra, where phi is the golden ratio. So 1 plus 1 over square root of 5 over 2, which is approximately 1.61. So it turns out that it basically grows exponentially, and you can approximate it very closely with just this kind of form. All right. So that was kind of just a mathematical diversion. So now how do we compute the complexity? Well, we do the usual thing, which is we try to count how many cols there are. So we start with fib of n, and then that produces 2 cols, right? So to compute fib of n, you need to compute fib of n minus 2 and fib of n minus 1. So that's going to be, this is n minus 1, and this is n minus 2. And then to compute n minus 1, you need n minus 2 and n minus 3. And to compute n minus 2, you need n minus 3 and n minus 4. And so on, up until the point where over here, you'll get 1. All right. So that's a picture of all the cols. So now let's say that I want to count how many cols there are. So we can do the usual trick, which is to try to compute level by level how many cols there are. So here there is 1, and then here there's 2, and then here there is 4. So here there is like another n minus 3, and so on, up until the point where at some point on the right-hand side, you start running out of cols, right? Because here on the right, you go n minus 2, n minus 4, n minus 6. So there's going to be n over 2 levels. On the other hand, if you look at the left branch, that's going to go n minus 1, n minus 2, and so on in n steps. So what you can say is that over here, it's going to be, in fact, 1, but it's going to be like at most 2 to the n. The usual way, the way we did it last time, like 2 to the 0, 2 to the 1, 2 to the 2, and so on. So here it's going to be at most 2 to the n, in fact, a lot less, because you're going to start running out of cols on the right-hand side, because on the right-hand side, this branch is shorter. But we can say and this, we already did the computation last time, so I'm not going to repeat it. This is the geometric series. So at most this many cols. So we can say, okay, like what's the upper bound on the complexity? Well, we can say it's O of 2 to the n. Now, in fact, it's a lot less than 2 to the n, because of this issue with we are overcounting, because the levels are going to be small. The levels are going to have fewer and fewer cols, because you're going to be running out of cols on the right-hand side. Does that make sense? Questions? So, okay, but that's an upper bound. So now we're going to do something that's usually not done and say, what is the lower bound? So what we can say is, let's just count the levels where it's definitely 2 to the k. So here it's 2 to the 0, and here it's 2 to the 1, and here it's 2 to the 2, and so on. So if we go just n over 2 levels, then all the levels are full. So there's going to be more than 1 plus 2, and so on, plus 2 to the n over 2. Which, again, we've done the computation, so that's 2 to the n over 2 plus 1 minus 1 cols. So there is more than that. So that means that a lower bound is O of 2 to the power of n over 2. Because the plus 1 doesn't matter, because the plus 1 here just means times 2. So that's a constant. So we can just say 2 to the n over 2, which is equal to square root of 2 to the n. Right? Just because 2 to the half is square root. So 2 to the half, that's 2 to the half times 2 to the n is 2 to the n over 2. So that's O of square root of 2 to the n. The square root of 2 is like 1.41. Do the quiz. New people, there's a quiz, go do the quiz. All right. So, okay. So we can say that this is kind of an upper bound, but maybe more than what we need. So there is like fewer than 2 to the n calls. And then this is like a lower bound. Yes. Yeah. Well, no, because what I said is we are going to count just the levels where we have definitely all of the calls on that level that are accounted for. And that's up to level n over 2, because at level n over 2, we're going to get to 1 starting from n and going in steps of -2. Right? So I can't draw out those levels because there are so many of them. But if you go in steps of -2, then there's n over 2 levels to get to 1. Right? And then this computation where I'm saying level 0 is 1 and level 1 is 2 and level 3 is 4, that's going to be an exact computation. Here saying that if I go n steps up, it's not really going to be 2 to the n because there's not going to be anything over here. Right? Because here I only go up to 1 in steps of -2. Make sense? So the interesting thing here is that if we go back here, so this is kind of between, and here's another approach that we can take. So I can say define the function make it k. So the number of calls needed to compute fib of k. And that's just like a mathematical function. And then I'm going to ask, well, what's n fib calls of k? Well, in order to compute fib of k, I need the call itself, the fib of k call. So that's 1. And then I'll need to compute fib of k minus 1, and then I'll need to compute fib of k minus 2. So how many calls to compute fib of k minus 1? Well, n fib calls k minus 1. Just by definition. Like this function just tells me how many calls it takes to compute fib of k minus 1. So I just plug in k minus 1. And then I also need this. So just mathematically, the number of calls needed to compute fib of k is this much. Why? Because the call itself plus whatever number of calls needed for this, plus whatever number of calls needed for this. Make sense? So now if you look at this function, it kind of looks like fib of k, except the +1. So you need to prove it rigorously, but it's basically equal to fib of k. So this recursive fib function has this weird property that the number of calls that are needed to compute it is actually the same as the function itself. The way we figured it out is we just said, well, like, what's n fib calls of k? Well, like, you need to compute fib k minus 1 and you need to compute fib k minus 2. So that's this. That's this part. And then we also need the +1. But those things are so much larger than 1 that the +1, as it turns out, doesn't matter very much. So the reason this is cool is because fib k is, we said, just mathematically, you can prove that that's phi to the k, phi divided by square root of 5 to the k. So O of phi to the k. So that means that here we have, well, it's less than this many cols, and it's more than this many cols. And in fact, it's exactly this many cols where phi is 1.61, which tracks because basically we have an exact estimate, which is like 1.6 to the n. And then here we said, well, it's more than 1.4 to the n, and it's less than 2 to the n, and 1.6 is in fact between 1.4 and 2. So it's all good. So this is like not an easy process any way you take it in order to estimate the complexity here, right? So you needed to draw the tree, and then you needed to say, well, I can't exactly compute how many cols in the tree there are because it's like a not nice symmetric tree. So what we did is just said, okay, like what about an upper bound on how many cols? And that was the computation for the upper bound. Yeah. Sorry, so the k is here. And then here it happened that we could do this kind of like mathematical trick where we said, well, it turns out that the number of cols, like we can write the formula this way, and this formula turns out to make sense. You can always write a formula like this. That's not difficult. Like it's always the case with a recursive function that you can just like write something like this where you say, well, like, well, not always, but like if you just always make this call, then, well, whatever is the arguments there, like if the arguments are n-1 and -2, just plug that in. That's not difficult. The difficult part was actually making sense of this formula, right? So noticing that this formula looks kind of like the formula for the Fibonacci numbers, and then also going and saying, well, we'll just ignore the +1 because we got to do that. You can mathematically prove that you get to do it. That would not be kind of not very easy, but it would be pretty easy. Or you can just try it out and see that the +1 doesn't really make a lot of a difference. But this analysis obviously kind of couldn't ask for you to do, for example, this part of the analysis on the exam, because like on the exam, like how would you know that actually you get to say that it's approximately Feb of k? You need to actually prove it that adding the 1 doesn't make a huge difference. One point that I'd like to make before moving on is that there is a huge difference between 2 to the n and phi to the n, right? So it looks like it's almost like a change in the constant. Well, and like, of course, not at all, right? So if you try to compute like the ratio between 2 and phi, and then so 2 to the n divided by phi to the n is like this. And this ratio, as n gets larger, blows up, right? So 2 divided by phi to the power of n, which is what it would be. And that goes to infinity. Right, so the ratio between 2 to the n and phi to the n is going to be huge for a large n. So, for example, would be this much for n equals 1,000. Right, so O of 2 to the n and O of phi to the n are actually like very different estimates, is my point. Does that make sense? So that's kind of as opposed to our usual idea that like 2n squared plus n compared to like 0.1n squared, well, they're different, but the ratio between them is constant. Right? So if n gets large, then 2n squared and 0.1n squared are also going to get large together with n, but the estimates are not different in the sense that the ratio is going to be constant between them as n goes as n keeps growing. So all right, questions? Okay, what's Discord saying? Wouldn't the upper bound be 2 to the n minus 1, not to the n plus 1? If we assume every reach the nth layer, there wouldn't be 2 to the n col, and like if the upper bound is 2 to the n, the upper bound is also 2 to the n plus 1. And in fact, like it's a lot fewer than 2 to the n as well. So I just assumed that the top level is full. Okay. All right, so the next point I want to make is that there is not, so even though we saw patterns in terms of determining the complexity of things, there is not a general pattern, and I just want to kind of show how it's not possible that there would be a pattern. If there is time on Wednesday, I'll actually prove it to you. For now, I'll just make a very suggestive example, and along the way, I want to do like one more coding example as well. That would help with that. To introduce this, so you'll see how that would make sense. So Fermat's last theorem is a to the n plus b to the n equals c to the n, has no solutions for n greater than 3 for natural ABC, right? So the idea is that for n equals 2, there is a solution. So for example, and there's multiple of them. So for example, 3 squared plus 4 squared is equal to 5 squared, right? So the theorem is that for squared, you can do it. For cube and above, you just can't. There is no solution. So that looks like a trivial statement. And in fact, kind of the history of that is, so Pierre Fermat, a French mathematician, was like scribbling on the margins of the book and stated this theorem and said that there is no solution for n greater than 3. And then said, I have devised a marvelous, or something like that in French. I have devised a marvelous proof of this proposition, but this margin is too narrow to contain it. So unclear whether he was just kind of trolling or whether he thought he had a proof or not. But as the case may be, until 2004, when Andrew Wiles published the proof, I think it was 2004, there wasn't a proof of this, even though it's true that there's no solution. So the point I'm trying to make here is you can actually write Python code that kind of depends on whether the theorem is true or not. And then because we know what the theorem says, we can say what the complexity of the code is. But if we didn't know the theorem, we wouldn't. The point is, well, I'll defer this until we actually wrote the code. So how to write the code to check whether the theorem is true? Well, you try all the possible solutions for a given n. So what I mean by all the possible solutions, like all the A's and B's and C's, the problem with that is, like, unlike with the passwords, where we had like a fixed alphabet for the passwords and we had a fixed length, here we don't have any of that, right? So A and B and C could be anything. So what we'll do is we'll do a trick. So we'll do Fermat, check Fermat K, and that would be nk. So return ABC such that A to the n plus B to the n is equal to C to the n. for A and B and C between 1 and K. And that function is easy, right? So you just try all the possible A and B and C. And if you find a solution, great. If not, you return none. So I'll just do that. So I'll say like for A in range 1 to K plus 1. So A goes from 1 to K. And then for B in range 1 to K plus 1. Then for C in range 1 to K plus 1. If it works out, so if A to the n plus B to the n is equal to C to the n, return ABC. And then here I can say return none or not because a function by default is going to return none one way or the other. So that I can just comment out. So now that I have this function, how do I check whether there is a solution at all? Well, I just keep increasing K. So I'll check this. And then if res is not none, I'll return res. And I'll just keep going. Right? So the way I avoided this kind of constraint that we had before when we were listing the passwords, that I have a fixed alphabet over which I'm going is I just say, well, just let me check ABC in the range of 1 to K, and then I'll just increase K and increase K again and increase K again until I find the solution. Right? So now I can just check. So I can check for mod2, for example, and I'll print the result. And here it found the solution. So for n equals 2, 3 squared plus 4 squared is equal to 5 squared. It found it easy. On the other hand, if I plug in 5, what's going to happen is an infinite loop. According to Fermat's last theorem, there is no solution. So it's going to keep looking for it forever. But in order to know that there is an infinite loop, where it's like 200 years of progress in mathematics that culminated in the proof of Fermat's last theorem, but up until that point, you didn't even know it was an infinite loop, let alone were able to say what the runtime complexity of this kind of function is, right? So the point is that sometimes, like even for something that looks quite simple, you can't even tell if it's an infinite loop or not. Determining the complexity can be, well, if you don't know if it's an infinite loop, obviously you don't know the complexity, right? And for some things you can, so for some things kind of math has made progress, and now we know. You would of course have to say, oh, like actually this corresponds to finding a counterexample to Fermat's last theorem, and that's how I know that it's an infinite loop. But in general, you would not be able, like there's no procedure for determining the runtime complexity of this. It took a long time and a lot of thought to figure out that it even finishes running. So in general, I don't know if there is time this semester. There is also just a mathematical proof of the fact that there is not a universal procedure at all for determining the kind of whether it's an infinite loop or not. So let alone determining what the complexity is. So the point is sometimes it's difficult. Of course, a lot of what you see on the exam is kind of patterns that you saw before. You just need to kind of figure out which of the patterns applies and maybe adjust the pattern a little bit in order to get the solution. So, okay. But in principle, it's like, so like people often ask me, like, tell me the recipe for how to figure out the complexity. Well, there isn't one, is the point. Or if there had been one, then you could solve like all of math because it would be a recipe for all. So, okay. So I want to switch to a situation where it looks like it's very difficult and there's nothing you can do, but in fact there is. And that's figuring out the kind of a fast sorting method. So this is called merge sort, and this is basically what Python uses for sort and sorted. And the idea goes kind of like this. So I'll make a largish list, which like looks like it's a chore to sort. So the idea for merge sort is I'll split the list that I have in half. Then I'll sort the first half, I'll sort the second half, and then I'll merge the results together to get one big sorted list. So this would be like 2, 5, 12, 20. And this would be like 1, 2, 6, 30, 50, right? And now that I have the two sorted lists, it's kind of should be intuitive that it's not that difficult to merge them into one big sorted list, right? So I just go whatever, like 1, 2, 2. And then I get the 5 from here, and then I get the 6 from here. And then I get the 12 from here, and then 12, 20. And then what's left is just the 30, 50 from over here, and I'm done. And if you were following along, I think it should kind of feel like it's kind of easy to do it. And in general, if something like if it feels like it's easy to do it, it means it's like low computational complexity. Right? And the insight here is if the list is small enough, you can sort it, like I could sort it just by I. And then if you have two sorted lists, it's not difficult to merge them together into one big sorted list. So that's basically the idea. So we'll say merge sort of L is what happens if you sort the first half. And then you also sort the second half. And then you merge the two halves together with this merge function. So that's the basic idea, kind of mathematically. Sort the first half, sort the second half, merge the two halves. And it turns out to be very efficient just in terms of computational complexity. So the first thing that I'll do is I'll write the merge function. So you could, of course, like if you just wanted to write something that's not necessarily super efficient, you could have just said like return sorted L1 plus L2. That fulfills the requirement, right? So you just stick them together and sort them. Of course, that's like slow potentially. So what we want to do is we want to exploit the fact that L1 and L2 are already pre-sorted. So how would we do it? Well, the basic idea is you just keep kind of what I did here, right? So you keep track of where you are in L1 and keep track of where you are in L2, and you fill in the result while keeping track of where you are. So here, like we're here in L2 and here in L1, so the element from L2 goes first. So now we are over here in L2, still over here in L1. So then we fill in 2 and 2. And now we're here in L1 and we're here in L2. So 5 is smaller, so we fill this in. So now we're here in L1 and here in L2. So 6 goes here. So now we are here in L1. So 12 smaller than 30. So that goes here. 20 is still smaller than 30. So 20 goes here. And now we ran out of stuff in L1 and we just need to get the rest from L2. So that's what I'm going to do. We're going to say, so the location in L1 initially is going to be 0, and the location in L2 initially is going to be 0. And I'm going to say, okay, so if the element at the current location in L1 is smaller than the current location in L2, get the one from L1, otherwise get the one from L2. Right, so if this one is smaller, append this one, and advance the location in L1 by 1, right? So next time, if we get something from L1, look at the next location. Otherwise, do the other thing. And then we just keep advancing. So when do we need to stop doing it? Well, we need to stop doing it before this just produces an error, because either lock L1 or lock L2 are now the length of L1 or the length of L2, right? So we don't want to crash. So that means that the condition should be that it's both the case that the location in L1 is smaller than length of L1, and the location L2 is smaller than length of L2. So if we are here, that means that we either ran out of elements in L1 or we ran out of elements in L2. Because like either lock L1 became length of L1 or lock L2 became length L2. Can't happen at the same time. It's one or the other, right? Because every time we advance either an L1 or an L2, not both. And initially we haven't run out of elements. But that's okay. That's all right. So what we'll do is we'll just say extend res with the rest of L1. So L1 starting from lock L1 and up to the end, and then do the same with L2. So what we're using here is that if you do the slicing, we are still trying to find the counterexample to Fermat's last theorem. As you saw, like we haven't. Because of math, this is still gonna run, and like my laptop is actually working really hard. That's part of why the battery was running out. And so we can see how hard it works actually. Yeah. Oh, I guess like not very hard. So 9% is CPU. It's okay. Yeah. Anyway, we'll put it out of its misery. It's not going to find a counterexample to Fermat's last theorem. And if you have a list that's like that, so L1 up to the end is 6, 7, but you can say like 100, whatever. If it's empty, it's empty, it's fine. So that's what we're using here is like one of those is going to be out of bounds. So either lock L1 or lock L2 is equal to the length of the corresponding list. That's fine. So it means that one of those is going to be empty. So we've been inserting elements element by element, and then there is like some left over either at the end of L1 or at the end of L2. And we're extending with both just in case, don't need an if statement. So, okay. So now we're done and we return res. So now the only question is, well, not the only question, but equation is, okay, what's the runtime complexity of this? So here we can say, well, how many times does this loop run? Well, at most length of L1 plus length of L2 times, because we're inserting elements from L1 or L2, and in fact, it's at most length L1 plus length L2 minus 1, because it's definitely the case that we're not going to run out of elements from one of them. But we can round up and say runs fewer than and then this guy creates a list of length less than length of L1 plus length of L2. Or suppose. And then extends res with that list. So that means runtime proportional. And that means runtime proportional. Right? So in both cases, it's a little bit less, in fact, but like basically proportional to length of L1 plus length of L2. So two things that both run in times that's proportional to the same thing. The whole thing is proportional to that. So that means that merge is O of length of L1 plus length of L2. And that makes sense. Like, what are we doing here? We're going through L1 and L2 together, and we're creating a list that's of length L1 plus length L2. We're going element by element, so the runtime is going to be proportional to the total number of elements. That's all we're saying here. It does look a little bit complicated, right? Because it's like a while loop and like, but kind of we look at the while loop and we ask, okay, what does each iteration do? Well, each iteration takes an element from one of L1 and L2 and puts it in res. So how many times does this run? Well, at most as many as there are elements. Make sense? Here, what we need to do is we need to create this new list. So that takes time, and then extend res using that list. But that list is of length at most length L1 plus length L2. In fact, it's like at most length L1 or length L2. But if you do plus, that's an upper bound. That's fine because it was already proportional to length L1 plus length L2. So, okay. So that's merge. So we can now write merge sort. In fact, we could do it before as well. So the base case is, well, like if the length of L is 1, then L is already sorted because a list of length 1 is sorted, right? So here we'll return a copy of L rather than L itself. And the reason is, like, it's not nice to sometimes return something that's an alias of something else. I don't want to return an alias of the input, because if the user then goes and changes that alias, that also changes the original input, and the user might not have intended that. So otherwise, I just break the thing in half. I already wrote it, so I just need to return it, right? And that's it. That's the function. So it's like very simple, assuming that you're fine with the merge function. And what's the idea? The idea is, well, in order to sort the entire list, sort the first half, sort the second half, merge the solutions. Now, we already had a sorting algorithm, so the nice thing about this is that it turns out to be really fast. So the analysis of why it's fast is going to be left until Wednesday. So it turns out that this is O of n log n, where n is length of L. So this, like much of other computer science, is so merge sort invented by, or like attributed at least to, John von Neumann, who invented a whole lot. And we might ask, like, however did John von Neumann come up with that? Seems difficult. So it's kind of like and kind of one answer as well. You have to be John von Neumann, maybe, but this is part of a general class of techniques that are called divide and conquer. And the idea is split the problem up into smaller problems, and then somehow combine the solutions to the smaller problems into the solution of the original problem. Right? And here the key was to say, well, like if you split it in half, then there is an efficient way of merging sorted lists, sublists into one big sorted list. So that was kind of the insight of John von Neumann. So if this sounds violent, well, if you go to John von Neumann's Wikipedia page, like that's nothing. The guy contributed to making the nuclear bomb and then advocated using it in all sorts of places. So like not anywhere close to the most, well, not personally, but not anywhere close to like conceptually the most violent thing. Anyway, so I don't know if he was an Oppenheimer or not. Actually, I haven't watched Oppenheimer. But if he wasn't, it's unfair to John von Neumann, who also contributed. Okay, so we'll get back to analyzing the complexity of merge sort next time. So course notes that are like not exactly the same. So kind of course all the lectures are posted, the video ones. So course notes and solutions to labs and stuff like that is also posted. You can also look at past exams, and I'll see you Wednesday. Thank you.